I'm here to present our work for semantic segmentation on Robust Vision Challenge. My group from University of Zagreb, we were second here. So the challenge here is training a single model on multiple domains, which poses some challenges. The first challenge is there going to be any interference of domain knowledge? And how much capacity does the model need to fit all of those data sets? So for this task, we had two objectives. The first one is to promote generalization on all of the test sets. And the second one is to address prediction uncertainty. This is particular for the Wildish datasets because it consists of out-of-distribution images, and also it is a collection of hard to classify images. So the model used for this submission is a ladder-style DenseNet, which is a follow-up to our previous work. Basically, it uses DenseNet 169 as a backbone, pre-trained on ImageNet. Our best submission on cityscapes gets up to 78% MIU on cityscapes test without the coarse subset. We used the 169 because we hypothesized we need more capacity. And to retrieve the resolution for the semantic segmentation, we use simple upsampling modules because they have enough capacity and less chance to overfit. And the original dense block 4 of the DenseNet was split into two parts, A and B, where we found that the increased receptive field helps with detecting larger objects. And we introduced the auxiliary loss after the last dense block. So here is the architecture of the model itself. So the top part outlines the original DenseNet with a modification of the fourth dense block being split into two parts. In between is the average pooling layer, which makes the DenseNet have a prediction at times 64 subsampled resolution. After that, we go to the context layer, which produces a prediction at times 64 subsampling, and here is the auxiliary loss. After that, we upsample the resolution using transition up modules, which I'll explain in more detail. And we have the final prediction at times 4 subsampled resolution, where the main loss is produced. So we made a few changes to the model for this task. We previously had concatenations, and we now use summations in the upsampling part, which achieves faster training. We doubled the number of feature maps in the upsampling part because we needed more capacity to fit on two different domains. Instead of the context layer, we use the spatial pyramid pooling because it produces the even larger receptive field. And we introduce a novel loss, which we called the pyramid loss, which we found generalizes well. So this is the changed model, and this is the submission for a robust vision task. So first you can see on the left the transition up module. Basically, it is a one-by-one convolution of DenseNet features, and it is summed with the previous transition up module, and the blending is done via 3x3 convolution. In the red, you see the spatial pyramid pooling layer, and in the gold, you see our pyramid loss. So at each level of the upsampling path, there is a prediction, a semantic prediction, at each at the different resolutions from times 8 to times 64 subsampling. And this is not a one hot cross entropy loss. This is actually a cross entropy between the prediction and the distribution of the ground truth labels in an image region. For example, for a times 32 prediction, we have a 32 by 32 image region, and we calculate the distribution of class labels in that area to, after that, calculate the loss. So the training data used for training the model is cityscapes train and val subsets, Wildish val, Kitty training subset, and ScanNet training for robust vision. The DenseNet 169 is pre-trained on ImageNet. So we did not use Cityscapes cores, Berkeley Deep Drive, or Mapillary Vistas for training of the model. To achieve a better class balance between indoor ScanNet dataset and the other outdoor dataset, we oversampled the driving datasets by 2 times. This doesn't produce a balance between the images, but it alleviates it, because we found in the preliminary experiments that ScanNet is quite difficult to achieve good results. So we give it a nudge for the ScanNet. And we found that mixing images from different datasets in a batch converges better than having batches of only one dataset. We hypothesized this is because we get batch statistic which better fit all of the dataset population. For augmentation, we use random flipping, cropping, and scaling. We use the Adam optimizer, and for the ImageNet pre-trained parameters, we have a 4 times lower learning rate. The pyramid loss contribution factor is 0.4. So the actual loss is a weighted sum between the main and the pyramid loss. So here are the main results on the challenge. We see that on Cityscapes, we have a 1% drop compared to our best submission. And on Kitty, we have a much worse result than Mapillary. This is probably due to the difference in scale from Kitty and other driving data sets. And on Wildish, we see that the negative detection of negative outer distribution images help a lot, which we'll show later. So to see how the pyramid loss works, we trained the model on Cityscapes only and evaluated it on Wildish and Berkeley Deep Drive at have the resolutions for better results, so for faster training. And we see that with using the pyramid loss, the model generalizes better. So it didn't see Wildish or Berkeley Deep Drive during training, and it produces better results on categories of smaller scale, like object, human, and vehicle. So here is an image on the left of a prediction using the pyramid loss and without using the pyramid loss during training on the right. So you see on the truck that the pyramid loss produces more consistent result. And we found that it generalizes better. But it doesn't produce perfect results. Here we see that on the road, we have bad prediction for the pyramid loss on all of the levels. So our model produces predictions for classes of Cityscapes as well as ScanNet classes, which makes 39 class predictions. So we wanted to see on the test set how much of the pixels from the driving dataset is present in scannet and vice versa. So we see that on Kitty, not a single pixel is predicted as scannet class, and on scannet, only 8 pixels are predicted as driving classes. On Wildish, we found that most of predictions for indoor classes is actually on negative out-of-distribution images. On cityscapes, we found the only image in test set which has a great proportion of scannet prediction. So you can see on the wall on the left, which is rather unique, that the wall is predicted as a scannet wall rather than cityscapes wall, which are 2 different classes. And on Wildish, you see on the top row the negative images. In the middle, you see predictions of the model. And on the bottom, you see in black classes which are cityscapes. So all of the classes which are not cityscapes, we predict to be out of distribution. And we found that on Wildish, it produces a 10% better result than without using out of distribution predicting. Also, we wanted to see how much does training on 70 images from Wildish improve performance on Wildish test set. We don't have qualitative results because we don't have labels on the test set, but visually we can see on the middle row, which is trained on Wildish Val, that the model produces more robust results, especially in the night images. So to conclude, we trained a common model on 4 datasets successfully. And we found that cross-domain training does not affect the model performance significantly. And also it helps with out-of-distribution detection. And our null pyramid loss alleviates overfitting to some degree. And I would like to thank the rest of my team, Sinisha, Ivan, and Petra, which worked very hard on this task. Thank you for your attention.
Okay, we have time for a few questions. I got one question. So, I mean, what's pretty interesting is basically when you train these things. So what I really like the idea of basically mixing data sets within a batch, which seems to help a lot, of course, because you're getting probably much more stable gradients.
Yeah.
I mean, if you're thinking about this, I mean, currently, I don't know, we have a couple of data sets. We have like 4 or 5 data sets right now, right? So if you're thinking about the future, if you're thinking about a larger variety, do you see there like automated ways of like figuring out how to figure out these distributions? I mean, I understand that right now we're just starting with robust vision, but I mean, for the future, we probably want to have some automated hyperparameter tuning in these kind of cases, right? What's your opinion there?
Yeah, this to detect. You mean by detecting other distribution areas? Yeah, this is a great area to explore, and I think that if you train the model on different domains, you have the space to produce predictions for auto-distribution, as we showed here. So if you, for example, if you have, let's say, 10 different domains, it is easier to find these auto-distribution areas, because modeling what the model isn't sure about is probably a great research area in the future.
Okay. Do we have any other questions? Yes. Come to the aisle.
Yeah. Could you explain a bit more about the pyramid loss?
Okay. So let's see the image. So as you can see on the main loss showed in blue, that we upsample the prediction by 4 times, so it matches the image size. And you see that for the pyramid loss, we don't have that upsampling. Instead of that, in the image region corresponding to that feature, the pixel of that feature, it actually represents a area rather than a pixel in an image. So we take a semantic label, the ground truth label, and for that area we calculate the distribution rather than a one-hot label. So you can imagine a boundary between the road and a car. So if you upsample that, you have some noise in the when training the model with that loss. Instead of that, if you have the distribution, you model all of these things presented in that area. I hope I answered your question.
So one thing that was not clear to me was, so in that pyramid loss block, right? Imagine you have, let's say, 20 classes that you want to predict. So
Yeah.
you get a kind of soft max. So
Yeah.
then first do you take the argmax, then compute the histogram, or that's the one that was not clear to me.
So you don't have to calculate the cross entropy with the one hot label.
Yeah.
So the cross entropy is the difference between the two distributions, and the ground truth distribution doesn't have to be one hot. So we take that idea to get a more robust loss for the upsampling path.
Okay.
Thank you.
Okay, we have time for a final question. Yes, in the back.
You showed an example where there was an image from the cityscape database.
This one?
Yes, yeah.
Yeah.
So is it possible that the pixels have, I mean, is it a yes or no decision that a pixel gets a label from, a class label from ScanNet versus Cityscape, or is it a kind of a softer distribution?
So for this challenge, the model had to produce all of the classes. So there is 19 classes from Cityscapes and 20 classes for ScanNet. And the model needed to have the same parameters, right? So we took that idea, and for Cityscapes and other driving datasets, we said, okay, if the prediction is from ScanNet, we treat that as a void prediction, rather than predicting it as a Cityscapes prediction. And in that way, we model the model's uncertainty. Okay.
All right, thank you very much. Let's thank the speaker again.